Good evening, guests, students, and colleagues. My name is Washington Ochieng. I'm the current head of the Department of Civil and Environmental Engineering here at Imperial College, London. It is my pleasure to serve as chair for this evening's event and to welcome you to this professorial inaugural lecture of our Professor Jamie Standing. Jamie is our chair in ground engineering here at Imperial. So whether you're here in person, joining us online, you are very, very warmly welcome here, and thank you very much for attending. I understand that some of you have traveled from as far away as Japan and Brazil to be here this evening, which is, as they say, fantabulous. Now, before I say a few words about Jamie, I say a few because I could speak all day about him. In the event that the fire alarm goes, please follow the emergency exit signs to leave the lecture theater. And the assembly point is on the corner of Exhibition Road and Imperial College Road. Please note also that this event is being recorded. So a few words about Jamie. So Jamie was born and raised in South London and completed his bachelor's degree in civil engineering at the University of Dundee in Scotland. He worked in industry as a geotechnical engineer with Fugro Limited before coming to Imperial College to study for a Master of Science in Soil Mechanics in the 1986-87 academic year. And some of his classmates, he tells me, are here tonight. So, double welcome. He then returned to industry to work at Over Arup and Partners, or Arup Geotechnics. He returned to Imperial in 1989 to undertake research, or his doctoral research, investigating the interface resistance of nails under the supervision of Professors John Burland and David Potts, who are both here this evening. He continued with his research work in the department with Professor Vaughan on arch embankments, Professor Burland, Jubilee Line Extension, and Professor Richard Jardine, driven piles. In 1999, he was appointed as lecturer at the University of Cambridge and a fellow at Downing College. Jamie returned to our geotechnics section. Yeah, he didn't quite understand what he was doing over there in Cambridge. I mean, he saw the light. And he returned to our department, taking up a lectureship in 2002, and he was subsequently promoted to senior lecturer in 2004. Then he learned how to read in 2015, and in 2021, he was made a full professor at Imperial College London. Now, during his time at Imperial, Jamie has established himself as an international leader in the field of full-scale field monitoring and the ground and structural response to tunneling. In particular, he has led 3 field research projects directly connected with key infrastructure projects which have required careful liaison and negotiation with project teams, industry and asset owners. And these projects include the Jubilee Line Extension, Channel Tunnel, Rail Link, and most recently, Cross Rail. Now, the outcomes from these projects have led to the publication of books and numerous high-quality research papers, some of which have been awarded prizes. These publications are also frequently used by practicing engineers in industry as well as academics. Jamie is a chartered civil engineer and member of the Institution of Civil Engineers. He has served on learned society committees, namely the British Geotechnical Association and British Tunneling Society, and is currently a member of 3 technical committees of the International Society of Soil Mechanics and Geotechnical Engineering. Jamie has also served on the editorial boards of Geotechnic and the Quarterly Journal of Engineering, Geology, and Hydrogeology. Now, most importantly, Jamie is an excellent citizen of our department and a much valued colleague. He was senior tutor from 2009 to 2013, teaching quality coordinator 2014 to 2019, and is currently chair of the Board of Examiners and the Promotion Committee for our technical, administrative, and professional staff. Jamie is also a keen member of our departmental library committee. Having said that, it is now my absolute pleasure to invite Professor Jamie Standing to step up and deliver his professorial inaugural lecture, which is titled Ground Engineering, Foresights, Insights, and Backsights. Thank you very much. Thank you.
Thanks a lot, Washington. Okay, many thanks, Washington, for your kind words. Many thanks to all of you for taking the trouble to come. I'm really honoured that you've come, especially those of you who've come from afar. And it's great for me to have my family, my friends, my colleagues, researchers, and even some of our undergraduate students here. Thank you so much for coming. Many thanks also to those online. I'm aware that many of you are in completely different time zones, and also I want to say a particular greeting to my family in Hong Kong. So let's get started. So lecture content, the site, as Washington just mentioned, foresights, insights, and backsights. Anyone who's done any surveying will sort of recognize these words as common terms for parts of a course during the survey. So here the foresights mean making predictions. The insights, rather than intermediate sights, as we would usually call them, refer to going out in the field and learning things in situ. And then the backsights is the ground response, it's sort of hindsights of what we've learnt. And I'm going to finish off with a very short section on future challenges. So, introduction and thanks. I think many thanks to many people. And it's very important for me to say this right now. There's so many people to thank. And it's been a long journey for me. And I've been very, very fortunate with many of the people I've interacted with, both staff, my colleagues, the students, my research, my fantastic researchers, etc. So thank you all very much. I must admit, I must thank Professor John Burland and Professor David Potts, my supervisors here in particular. They've put up with me for goodness knows how many years, and I'm still hanging around. And yeah, I also want to extend thanks to Robert Mair, Professor Robert Mair at Cambridge, actually, just because, for interacting with him before, during, and after the Cambridge days. I also want to mention Finn Jardine. Finn, I got to know during the JLE works, which you'll hear about. And yeah, I've learned so much from you, Finn, and greatly valued your friendship. There are many, many others to thank. I want to particularly thank our excellent technical staff. We've got Steve and Les who are here, Graham, who's here, Alan, Prash, Luke, Steph, and also Sue and Jess. Thank you so much. Before I start formally, I also want to make a particular thanks to Professor Peter Vaughan. So the title I have, Professor of Ground Engineering, was Peter Vaughan's title, and I'm really honoured to have the same title that he had. It's very big shoes to fill. Right, let's carry on. So what do we mean by ground engineering? Well, first of all, I want to say that in this lecture I'm going to be talking about the ground as relating to soils rather than rocks. And we can ask ourselves, what exactly is a soil? And why do we need to engineer the ground or the soil? And what are the things we need to think about? Well, in classic texts, there are four elements that make up all matter: fire, earth, water, and air. Fire, igneous rocks come from magma. Igneous derived from the Latin word ignis, for fire. Magma, ancient Greek word for thick unguent or paste. And ash, the remains of matter after fire. And particularly relevant to mention today on Ash Wednesday. Water. This is what we need to sustain us, and which can also weather and transport soils. And air, this is what we need to breathe, and it can also weather and transport soils, the lighter ones, of course. And the earth, well, the earth is the solid remains from the weathering of rocks and of ash in particular. So many of our active clays come from the weathering of ash. So soils are derived from fire with the help of water and air. They are particulate and potentially comprise three of the classical elements: earth, water, and air. This makes them very different to many civil engineering materials. And also, the soils have three phases rather than just one. Two of these phases, the water and the air, readily intermix with each other. So understanding their behavior is challenging. Why engineer the ground? Here we see the shard, Tower Bridge, the Tower Bridge piers, and a berthing jetty here. They all sit on piles. For the shard, they sit on very deep bored piles extending down to the Thanet Sands. The Tower Bridge piers probably timber piles, and then we see these steel tubular piles driven in. All we need to think about what capacity they need to take, how much they're going to move, etc. Embankments. Years ago, embankments were formed simply by dumping fill material like this. This is excavated London clay, probably from tunnels and from excavations, and no compaction. And as a consequence, a lot of these embankments suffered a lot of deformation and displacements, and also instabilities. And one way that was used to remedy this, to keep the alignment, you don't want things moving if you've got trains running on them, was to top them up with locomotive ash. It's light, it's a waste material, and it's got good frictional properties, and it's free draining. And I'll talk a bit more about that later. Modern dam construction, in this case an embankment dam, the Ilarion Dam in Greece, we can see the nicely colour-coded central core and filters, so very much engineered as necessary. Moving on to tailings dams, I was very fortunate to be part of a team with my eminent colleagues, Michaela Jamolkowski, Cara Herg, and David Carrier, and who before was Dick Chandler was there also. This is a picture of the dam that we worked on, the Żelazny Most Dam in Poland. It's 14 kilometers around its circumference. It's enormous, and it's about 70 meters high in places. And I very much enjoyed this work. I learned a lot from it, and particularly with the interaction of my colleagues from Geoteco and KGHM, the mine people, and you see us here. Here we're about to descend about a kilometre from where the ore is extracted, and the photograph obviously taken from about a kilometre above. And then tunnelling. This is a subject dear to my heart. So this is one of the TBMs used on the Channel Tunnel rail link. And at this point, let's just mention this was for a project where we were looking at the influence of tunnelling using machines like this. You can get a feel for the size. It's about 8 metre diameter on existing piles. And here we see zones of influence. This work was done with Dr. Demetrios Selametas, following actually work from now Professor Esfia Jacobs and Dr. Gary Choi, who had used centrifuge modelling to look at the effects of tunnelling and diaphragm walls on existing piles. And we continue actually with the piling theme. One of my current researchers, Clive Appleyard, is looking at the piles that were intercepted and cut into at the bank station upgrade. Moving now to shallow foundations, equally important. You can see the damage that's been done to these structures. These structures are in an area close to Khartoum in Sudan, and my researcher, Dr. Louay El Hussein, did research looking at collapsible gravels. And a few years earlier than that, Dr. Khalid Al-Haj, who I'm very pleased to see here also, did work on another Sudanese troublesome soil, very expansive soil. And then we come on to deep excavations. Often our work involves safeguarding historic structures like the Palace of Westminster, and in particular the Big Ben clock tower. So this is pre-JLE, there's no Westminster station there. And this is what they wanted to build, and which they did build. So this is the Big Ben clock tower. This is one of the deepest excavations in London. These are the running tunnels that went past and open up to station tunnels. All of this had to be done without excessive movements on Big Ben. It's a fantastic engineering feat. And just to give you an idea about the scale, this is taken somewhere near the base of that excavation. And you can see these props. These props are solid steel to try and minimize the movements of the diaphragm walls encasing the box. And we want to make predictions, and we want to make accurate predictions, and this is the sort of thing that we want to avoid. And this prediction was actually made by people at the Evening Standard who clearly hadn't been on our MSc course. So what do we need to think about? Well, in order to engineer the ground, we need to understand the materials that we're dealing with. We need to obtain an idea of what's in the ground through geological records and in situ investigations. And characterization often starts in the lab. Now, I'll be back in just 2 ticks. And this is more my modus operandi, really. So soils are classified in various ways, but fundamentally by the size of the particles. And what we've got lined up along the front here are 9 beakers with these different materials in them. We've got, at the far end, your right-hand side, we've got the coarse gravel, just one big lump. Gravel, so gravel's in these, coarse, medium, fine. Then we've got the sands, coarse, medium, fine. We've got one silt, and we've got kaolin and montmorillonite. So they've got exactly the same mass. Each of them has 100 grams of material in. And what you can see straight away is that some of them have completely different volumes to others. So we see here, for example, the sands and the gravels all have roughly the similar volume. By the way, I didn't measure them and estimate them in these beakers. I did measure them using a measuring cylinder beforehand. The silt a bit higher, but then we look at the kaolinite and the montmorillonite. Why are these bulking up so much? These materials are clay minerals and they have a net negative charge. So these are controlled by electrostatic forces rather than gravitational. So all of these, you can definitely hear a granular, I won't do it with that. And you might ask, why this one? This one actually is less active than this, and it's just to do with the grinding process. So we've got these we would refer to as colloidal. These we refer to as gravitational. And the silt somewhere in between, this particular silt probably on the gravitational side. What do these fine materials look like? Well, we've got kaolinite and montmorillonite here, 10 microns here and 1 micron here. These are very small particles. Can you see the pointer? Yeah. So often with these, we're talking about scales of down to about 10 nanometers. And how do we express these sizes? Well, we express these sizes, the gravitational ones, we determine the size by putting them through a series of sieves of decreasing aperture, and we measure what's retained on each of the sieves, and then we measure the percentage passing. So up here we've got fairly steep curves of the sands and the gravels, and then we've got the silt, the kaolinite and the montmorillonite. So we can see that this, and these two are measured not gravitationally, they're measured through sedimentation processes. So if we extend this down here, would be about 1 nanometer. If we consider cobbles and boulders, we'd be up to about 1 meter. So we've got 9 orders of magnitude. So we talk about very wide-ranging quantities in soil mechanics and in geotechnical engineering. That's something equivalent of comparing a pea with the size of the moon. It's something of that order. One quick picture from our undergraduate field trip. So here we've got the whole range of soil types. Think about dropping them in water. If we drop the gravel or the sand into water, they'll sink very quickly. The silt will also sink. But the clays, especially the active ones, will float around, controlled primarily by Brownian motion. So we need to think about the timescales involved. It takes tens, hundreds of thousands of years for these materials to settle. Continuing on with characterization, in soils there are potentially 3 phases: solids, liquids, typically water, and gas, typically air. That particle size distribution curve only gives us information about the solid content. It doesn't tell us anything about the size, it only tells us about the size, doesn't tell us anything about the shape, and certainly not the state. So the phases, the 3 phases, are often pictured using these phase diagrams. So we have air, water, and solid, and we can express them either in terms of mass or in terms of volume. Besides size, we need to think about the other 2 phases and the state. There are several other factors to take into account, so we need to introduce some measures of state. So the first one, perhaps the most fundamental, is water content. It's the mass of water over the mass of solids. Let's take the kaolin sample that we have here, and let's add different amounts of water to it. So 66 grams, 49, and 32, and then we've got our dry one. So that gives us our water contents as we see here. If we think about it in terms of volumes, then these are the relative volumes. We've got some air creeping in to the 32, and as we know, the dry one has no water. And these water contents are particularly chosen because they represent the liquid limit. If we wet it up any more, it essentially becomes a liquid, and the plastic limit. If you dry it out any further, the soil starts to crack and fall apart. And what I've done is prepared 3 samples at those 3 water contents. So here I've got the liquid limit. It's a bit like a yogurt. This one, dare I take it out, that's at the plastic limit, so you can just about shape it, and it's certainly got some air in it. And this one is quite sticky. So 3 really quite different consistencies. This has got some stiffness to it. This has probably got very little strength, and the one in the middle somewhere between. Another measure of state is the void ratio, the volume of voids to the volume of solids. And here we again can see the differences. All of the sands and gravels over to your right all have very similar void ratios, roughly. The silt's a bit higher, but then we come back to these 2. We've got the kaolin. It's got 5 times more air than it has solids, and the montmorillonite about 2.5. And the third measure that I want to introduce is the degree of saturation, the volume of water over the volume of voids. And actually these 3 quantities are linked together. The water content times the degree of saturation is equal to the water content, times the specific gravity is equal to the void ratio times the degree of saturation. Right, so let's think about what happens as the soil dries out from a fully saturated state. So we'll start at 100%, not observe what happens as it reduces. Now the behavior of the gravitational and the colloidal is completely different, so let's look at them individually. So here we've got a fully saturated sand particles, degree of saturation 1, and then as we start to dry it, we get a meniscus pulling in on the surface, we get small occluded bubbles starting to come in. If we continue further, the meniscus pulls in further and the bubbles start joining up together. They coalesce. And eventually they coalesce sufficiently so that we've got continuous air phases and continuous water phases. Eventually, the water dries out such that we've only got meniscus water and we've got continuous air. And if we dry, we'll note that that's at about a degree of saturation of 0.2 roughly. And then if we dry it out fully, in the case of a sand, it would dry to 0. So let's now have a look at the differences of these water contents and degrees of saturation. So we've got 3 of the medium sands here, 100%, 20%, and dry. I hope these haven't dried out since I've mixed them up. There's always a risk. But so let's try the fully saturated one first. Well, that one must have dried out a little bit, okay. Let's now try the dry one. Hopefully this one will be all right. That one, we've got a very poor heap, which reflects the angle of repose. And this was the one I was expecting to be more like that. It is. It's a better sandcastle, you've got to agree. But we see the difference, completely different. This, I would expect to slump a bit more, but there you go. Let's move on to clays. So starting off with a fully saturated clay, the first thing to say with clay, if we put the clay in water, because it has this net negative charge, it attracts cations from the surrounding water. And you have what we refer to as an adsorbed layer of water. So that's right next to the surface of the particle, trying to counter this net negative valency. And then there's an absorbed water layer that you can't attract enough. There's not enough space on the particle surfaces to fully attract it. So we have these different types of water. And again, as it starts to dry, we get some occluded bubbles, but at much higher water contents. The boundary meniscus moves in, and the particles start grouping together to some degree, and they form these clay packets. And eventually, we have clay packets that are surrounded by menisci, are held together with menisci, and eventually the menisci go. So we've lost most of the bulk water. You can see we can't dry these out completely because that absorbed water is held quite tightly by the clay particle charge. So our phase diagrams actually take a series of steps as we desaturate here. And in the case of clays, it's actually much more complicated. Usually we just express them with this sort of thing, air, water, and solid. But when we've got clays, we've got adsorbed, absorbed, as well as potentially meniscus water. And this is very significant. If we compress this, so we squash the water out of it, eventually we squeeze out most of the bulk water, and we might start then impinging on that absorbed water. And it also has very important implications if the water has any salinity in it. So a former researcher, Dr. Hendarto, who looked at water extraction in Jakarta in Indonesia, and as the water was extracted, the water table came down, this is over decades, and the seawater started to come in, and that salt water coming in provided the cations that were needed. So the adsorbed water reduced, the void ratio reduced, but because there was more bulk water, the permeability increased. Completely counterintuitive to start with. The other thing just to mention is soil water retention curves. We've got degree of saturation that we've just defined, plotted against, again, a log scale of matrix suction. As these soils dry, the water goes into negative tension. So we've got a suction in. The suction defined as the air pressure minus the water pressure. So you end up with a positive value. So at this point here, we can see the sand is starting to desaturate, and this is the air entry value. For this sand, typically 2 to 3 kPa. For clays, it can be a megapascal, it can be several megapascals. So you can impose very significant suctions before it desaturates. So we've looked at some fundamental characteristics on a a wide range of soils and the effects of air and water on them. How are these characteristics and states reflected in what we observe in the ground? The characteristics often remain the same, but the states vary enormously depending on the history of the soil. Let's consider the London Clay Formation. Everyone knows I had to mention London Clay, didn't I? So this is a piece of London Clay, and it doesn't look anything like any of these. It's much denser, it's stiff, I can just about get my fingernail in it. And why is it so different? Well, this material was formed about 55,000 years ago. This is a slide from Dr. Chris King, who I was greatly privileged to work with on several occasions, along with Dr. Jackie Skipper. And Chris did a phenomenal amount of work on the London clay that many of us were not aware of until much later after he'd done it. So this is work from the 1980s. At this time, 55 million years ago, a large part of the southeast England was covered by the London Clay Sea. But the important thing is the shoreline was transgressing and regressing. So you get different depths of water. So typically, these soils have a coarsening upwards gradient. We call this sequence stratigraphy. So Chris looked at the sequence stratigraphy, and he came up with 5 divisions, which are still used today, 5 divisions within the London clay, which have quite different characteristics. The other way that he classified them was through the use of micropaleontology. And you can see here, there's a list along here of mostly unpronounceable names, varying with depth. And you can see that some of these little creatures, these are microfauna, lived at different times and are evident at different depths. So here, this Cypsidoides existed for all of this division B and A3, whereas this one, I'm not going to try and pronounce it, there's a lot of them, but only occurred at that one time. So this is the Cypsidoides one, the one that pops up everywhere. Looks like a bit of rotten pancake from yesterday, doesn't it, really? This one, I'm not going to try and pronounce, but just to show you what it looks like, it just amazes me that you can find things like that in a lump like this. This is Will Mannion's work, along with Dr. Mike DeFraser. Very happy to see you here tonight, Mike. And this is another one. Again, I'm not going to try and pronounce it, and I might cause some offence if I try, I think. So we talked about the 4 elements. Besides the 4 elements, we have a 5th one that is often the case in soil mechanics. So that's the element of time. So let's investigate some in situ soil states and also how the ground responds to engineering activities. So let's go on to field characterization and monitoring. Before I do, I just want to say a couple of words about tunneling. So if we construct a tunnel moving along here, let's say it's at 20 meters depth, it's got about 400 kPa on it, about 40 tons per square meter. And of course, if you make an opening, the ground starts to move in towards that opening and you cut into it. And that manifests itself at the surface as a settlement trough. Here we've got something approximating a Gaussian curve, that's the transverse one, and then the longitudinal one here. So we expect to see these settlement troughs. This is the tunnel boring machine currently being used for the crossing to Silvertown, the Thames River crossing. And thank you very much, Ivor, for coming and for providing the photo. And let's just move on to this while they're just popping out for a moment. Right. Many of you will probably recognise me in this attire, so we need to get ready now. So you saw here the clip, again, thank you very much, Ivor, for the clip of a TBM. Maybe just talk through it briefly, sorry. So here, you can see the spoil coming out from it, swiveling around. This is the Archimedes screw where the spoil comes from. You can see the lining, looks beautifully constructed actually. You can get a feel for the scale of the thing. The cutter head is hidden in the front here, and all of this and the lining erections being controlled by a very small number of people. Right, I want to start off at St James's Park. This is one of the sites that we used as a control for the Jubilee Line extension works. This is work from Dr. Rob Nyren, and Rob, I think you're listening in. You'll be amazed at how often your name gets mentioned. So, here's the edge of St James's Park. Here are the two running tunnels. We had a lot of instrumentation in this little triangle here. And this was the settlement trough. I mentioned that Gaussian form as the first tunnel came through. I mentioned, so we've got about 20 millimetres of movement. That doesn't sound very much. The driller who installed the instruments, I bumped into him a few years later, and he said, "Oh, what happened at St James's Park?" And I said, we got 20 mil of movement. He said, "God, I could have done that with my heel." But the significant thing about this is that the volume loss was 3.3%. Now, that number may not mean much, but all the calculations were done for the predictions for how much the ground would move, assuming it would be 2 at the maximum. So this was a significant excess over that. And what we also noticed was that we had these very large volume losses. This is for the first tunnel, this is for the second. But north of the lake, they were much more what we would expect. As a consequence of that, and in order for us to try to get a better understanding, we drilled 5 sets of boreholes to look to see. We knew the tunnelling had some influence, the way that they were operating, but we wanted to check the ground conditions. So here's our St James's Park site. We've used 2 other sites here as well. And the first thing that we noted was that the top of the London clay was 4.5 metres shallower south of the lake compared with north of the lake. So this material had been eroded away along with the Kempton Park gravels, and then probably for tens of thousands of years the ground was swelled and then new material was dumped on top of it. We took all those cores, we laid them all out, we described them, incredibly tedious and very, very difficult to look subjectively at this and to look objectively at this and to try and ascertain whether there were differences. But we also plotted and measured water contents, and we see the water contents here. And if we look here, we can see there's a sharp drop there coming down here. Then there's another sharp drop. We can also note that the water contents south of the lake are a bit higher than those north, so likely to be softer. And we asked Chris King to come, it was the first time I met him, to look at those cores. He walked up and down, you could see them all laid out, and he said, that's where Division B finishes, that's where Division A3 starts. And they corresponded exactly with the breaks that I'd made here, which was really one of the most satisfying things I've had. This division here I put into it because you'll see why in a moment. So we've now got this stratigraphy within the London Clay Formation. This is the B division, the upper one. If you get your eye in, you can see the fissures there. Directly beneath this, the division A32, this is the one with the siltons. This one has silt and sand partings, very important in terms of permeability. So this is why I split this up. If we look beneath it, we see that it's faintly laminated, but no silt and sand. And then division A2, it's a mix. At the top, it's bioturbated, been chewed up by worms, further down into beds of sands and clays. So now let's superpose the tunnel alignments. We see that first tunnel coming through here. It's got its crown in that A32, the one with the silt and sand partings. But as it comes up here, it's coming out of it. Equally, the second tunnel's got its invert and that axis almost in it. but by the time it gets to the other side, it's coming out. So those tunnels would have been affected by that substratum. And another amazing thing to me was that during the drilling works, I asked the drillers to make a note of the water strikes. And you see them here. They correspond exactly with this A32. And the driller on the south had all sorts of problems with the stability of his borehole. So immediately that should tell you that there's something awry. And I've put this little schematic together. So here's our silt and sand passings. There's fissures there as well. We know they're under pressure from the water strikes. If we then relieve the stress from the tunnelling, the ground moves in. There's much more blocky movement. Talking of fissures, I just wanted to mention fissuring in London clay. This is work that was done by Skempton in the late 1960s, but just to show you what it looks like. It's pretty much sub-vertical. And I also wanted to mention some work that I did when I was an undergraduate with Robert Craig. Very honoured to have worked with him also, looking at fissures in Errol clay. Let's move on to Crossrail. This is, a lot of this work is work from Michael Wan. I'm very glad to see you, Dr. Michael Wan. Very glad to see you here. We know the Crossrail alignment, so this is where our site was. And more specifically, the Crossrail tunnels came in through here. We had our instrumented site in here. And actually what we were particularly interested in is the effect of tunnelling on existing tunnels. And these are the central line tunnels. So here's the Crossrail tunnels, here are the central line tunnels, all in London clay. And I think in this section, one of the things I want to mention is that making these measurements, we need to make holes in the ground. We've got discrete holes, we've got anchors at different positions, and we need to tie all of this together. And it's not easy work even making the holes and getting accurate measurements. So all the crosses here are points where we've got anchors where we can measure vertical displacements. These are where we've got devices for measuring actually rotations that we integrate to form horizontal displacements. And here we've got piezometers. And this is the sort of work we're doing. We're out in the field surveying. These are good weather shots. We don't take pictures when it's pouring with rain. And equally, this is taking measurements with Dr. Jessica Yu, Dr. Weiwei Sim, taking measurements on the extensometers. Again, it's nice and dry and, sunny. And let's also think about these tunnels. Again, huge tunnel machines. And we were interested in the effect of driving that underneath the existing central line tunnel. So with our colleagues from ETH Europe under Professor Sasha Puzrin, we installed fibre optics. We installed our own instrumentation. This is Duncan Parker, who was a great team member, putting in strain gauges. And we also wanted to try to understand the behaviour of those segmental linings. Very complicated because of the fact that they've got joints within them, so they articulate. So we had specially cast grey cast iron segments manufactured using a Victorian recipe, and we put them together. This is Dr. Jessica Yu's work. So here's the ring. This is a reaction beam, and these are all actuators. We're controlling this using load and using displacements. And we did all of this. This all came from scratch. It was all designed by us, and it worked. It worked. We got fantastic data from this. So it was Jess, and then later Dr. Shada Ashfan continued that work as well. And this work at the time, Dr. Katerina Tiampusi was modelling this using IGFEP, and that work has now continued on recently with Dr. Agustin Ruiz-Lopez. So this work still, the data from this being used extensively. Going back to Demetrius's site, so this is sunny Dagenham, and these 4 blocks of concrete, these are loading those piles. And here again, just the instruments that were put in, not as comprehensive as Hyde Park, but this is the sort of thing that we're talking about. Drilling holes, you can see a part of the spoil here, the grout, it's all needed, and it needs to be done carefully. Work that I did with Professor Richard Jardine. Richard, thank you. And this was along with Eric Parker from Dapolonia. it was Eric's idea to look at these jet grouted piles, so have a pile and create a great big jet grout bowl beneath it. And we also used the opportunity, with Richard's wisdom, of looking at cyclic loading and the effects of time on driven pile resistance. This followed on from Dr. Fiona Chow's work a year or so earlier. So these are the setups for testing these piles. This is the control pile, massive beams loading up to 285 tonnes, and an even stronger arrangement for the jet grouted pile, reaching just over 500 tonnes to fail this pile. And then the ash embankments. So this is work with Peter Vaughan. We installed 3 boreholes, different angles, so that we could see the whole mechanism of behaviour. Within these there are electrolevels, and we've got tensiometers to measure the pore water change. And again, very tricky. This is a platform on the embankment slope with a drilling rig to put all of this in. What you usually see are all the nice data plots. You don't see all of this side of it. Right, so just another little detour. So what I showed here, what I wanted to show here was this phenomenon of arching. So I've got a stressed set of little pseudo particles, and first took those concentric circles out and then started picking them out. And we can see here we've got arching taking place. And then I took out a key piece and it all collapsed. Right, let's now get on to the fourth part. So an important thing to say is the interaction between the groups within our section. So we've got the lab, the numerical, and the field, and we all feed into each other. I want to mention a particularly interesting case, I think, oops, forgot about that. Usually got it on. This is talking about gas blowouts during the ground investigation for Thames Tideway. This was connected with Dr. Tim Newman's work. So they had blowout on at least a couple of rigs, and massive blowouts. And the gas, moreover, was found to be anoxic, and that was Tim's remit, was to look to find out why. You can ask Tim about that. And where did these blowouts occur? The blowouts occurred at the base of the Lambeth group. Base of the Lambeth group is granular. Thanet Sands obviously granular, and then there's impermeable material above. And why should that gas be there? Well, if we look at the London Basin from about 200 years ago, it's fed with water from the North Downs and the Chiltern Hills, and in the 1800s, the water was artesian. So when they put up Nelson's Column, all the fountains there were powered by artesian water. Then during the 19th and the 20th century, there was a lot of water extraction from light industry. It dropped down into the Thanet Sands. So those Thanet Sands, remember, would have desaturated. They would have desaturated and gas would have formed within them. And if we look at go back to these water retention curves, so this would have happened very readily. In the clay, it can sustain much higher suctions before cavitating. So when the water started rising again, which it did after the industry started moving out of London, that gas would have been trapped underneath the impermeable layers of the Lambeth group and the London clay. So as the water moved up, the gas would have gone under pressure, and then you penetrate it, you release that gas, and you get the blowout that we saw. Ground response to tunnelling. So just to say very quickly, when you're constructing a tunnel, the cutter head, you get ground movements in here, You overcut here, the shield is tapered, so you get ground movement in, and you get more movement out towards the end where you've got tail skin grouting and the lining erection. This is Michael One's work again. So these are two typical settlement profiles that we see here, much smaller volume losses, less than 1%. And then this is the sort of information that we can get from these subsurface instruments. So we've got extensometers here, and we can see that as different depths, this is the one just above the tunnel crown. As the tunnel approaches settlement, it starts moving in, then it goes up as they do the tail skin grouting, then it comes back down again. So it allows us to understand the mechanisms of the tunnel boring machine very well. If we now take these two inclinometers, either side of those two boreholes, we can see again we get a drop in movement followed by a rise and then a drop again for both of the tunnels. And we can see that here. So as the cutter head approaches, it starts moving in towards the tunnel, then it moves in, and then it moves back out again before moving in once more. So these complex mechanisms of movement. Once we have the horizontal and the vertical displacements, components of displacement, then we can draw the resultant vectors, and we can see these focal points that form. So here we see a clear contracting inward displacement field. The ground is moving in towards the tunnel. If we look here, this is from Demetrius's work for the CTRL site. Here we had the opposite. They were moving outwards, and we now realise, having looked at several case studies, it's all to do with the depth of overburden and the tunnel face pressure. Let's look at the piezometers now. Again, very interesting responses that you can link up with the tunnel progress. So as the tunnel comes in, let's look at this one just below the tunnel axis. We get an increase followed by a decrease. So increase as the tunnel approaches, then a decrease as it goes past the cutter head, then an increase from the tail skin grouting, and then another decrease as it comes out the tail skin. So we can characterize these in terms of pressure rises and pressure drops. And using this information, we were able to establish these arching mechanisms within and around the tunnel. So there's an arch in the front. What do we mean by arching? Arching is a redistribution of stress that may have been uniform to start with, and we get these arches. So we've got an arch here in the front, we've got another one like a barrel here, and another one beyond. And what's the significance of that? This is work that I did with Teresa Lung many years ago, looking at, this is a photoelasticity image. As we push a pile in, you see these light force chains, and as if I rotate it 90 degrees, we can see that they're attracted to the stiffer tunnel. So if we've got arching, we've got these lines of thrust, they can interact with the tunnel and deform it. And let's have a look at instances of that. So here we've got the existing central line tunnel. This is the crossrail tunnel. These are, again, measurements from Jess. We see that as this went past, the tunnel stretched in this direction. It elongated. That was when it was 8 meters away. When it was much closer, it elongated more. So this time it stretched in this direction, stretching down by just over 3 millimeters. Doesn't sound much, but actually these movements can have a very profound effect on the bending moments, and that's what I've mapped out here as well. And then finally, linking with numerical analysis, this is Vasilis Avgarinas' work. So here we see the crossrail tunnel approaching. Here's the central line tunnel, and here you see this elongation as the tunnel approaches and goes beneath, and also the absolute displacements, which are not so easy to monitor. Ash embankments, this is the last one. So these are the points we put in. Many assumptions need to be made to interpret the data from these. And these are the sort of results that we get. And again, if you'd seen all the mud and the foam and all the aggravation we had putting these in, and especially with the grouts, these are the plots that we get. Very, very instructive. And we can then put things together to understand the mechanisms of movement. There were two sites. This is the High Barnet one. There wasn't much ash, but this is one at Roding Valley where there were very great thicknesses of ash and much greater movements. And from these, we were able to interpret and determine how the ground moves at different times of the year, expressed here as soil moisture deficit. So in the winter, you've got menisci forces holding the particles. These soften up. In the summer, the meniscus forces disappear. They run down, especially with the train vibration. These shrink, but they move down. So you get spreading of the embankments. And this is one of the remedial measures that London Underground implemented to prevent this movement, because those movements cost, I don't know how much, but every year they had thousands of tons of ballast inserted to maintain the track alignment. I'm going to finish with long-term movements. Back to St James's Park. This is work that's been ongoing for a while, but this is work that Hun Young has been helping with since her fourth year project. Very glad that you're here now doing research with us. And these are the extensometers at St James's Park. I'm going to show you profiles from this section here, not the ground surface, because the ground surface is affected by trees, vegetation, etc. And I'm going to look at this position FX, this extensometer FX. These are the profiles. This is after the first tunnel went. There's the 20 millimeters. Then there was about 8 months, I've got consolidation settlements of about 10 mil. Then the second tunnel came through. We're now at about 37 millimeters. And then if we go down to 98, 2 years later, it's moved down. Just over 10 years later, it's moved down still. So this is 2009. 2021, last time we went, we've got total movements of 140 mil. It's about that. It's a lot. This site is about 100 yards from the Treasury. We all know we won't make any comments about that. But this is the F line, and you see initially there was more movement at the base, but with time they've all converged together, and we can see that finally it is flattening out after 22 years. I want to get one more set, and then that'll be it. So again, just to emphasise the importance of these interrelations, identifying future challenges in ground response. So permeability is very difficult to measure, and this is something that many of us are very interested in trying to pin down better. Fissures have a big influence on this, and I'm working on fissuring and actually bulk modulus with Jaime Wilsanin, who's here with us, one of our current researchers, and creep. Those movements at St James's Park, they're not just from dissipation of excess pore pressures, there must be an element of creep in there as well. And then, of course, there's unsaturated soil behaviour, and there's thermal behaviour, and we're working on these together. I want to mention Vasilis Mantikos, who's here tonight. Vasilis did a lot of work on unsaturated soil behaviour in relation to using it as nuclear buffers for the storage of nuclear waste. So hopefully from this, you've gained some insights into ground engineering. Hopefully you've learned some fundamentals of soils, even if not all the tests went right. Hopefully you realise the need to characterise in the field and monitor ground response to understand the responses. And I hope one of the things I really want to get across is that you understand the care that's needed to translate all aspects of the field work, the installation, the monitoring, the construction activities, to turn all of this into meaningful graphs and observations. And I hope you've hopefully seen how the ground and structures respond to tunnelling and other actions, and appreciated the essential need for teamwork and to interact with various disciplines and parties. Final thought, reflection on time elements. You know I like talking about orders of magnitude. Speed of light, 300 times 10 to the 6 metres per second. Speed of sound, 343 metres per second. What about rates of flow of water through fully saturated soils? Through granular soils, typically 10 to the minus 3, 10 to the minus 5. Clay soils, 10 to the minus 8, 10 to the minus 12. That's saturated. Unsaturated can be down to 10 to the minus 20. So we've got not just orders of magnitude changes, we've got orders of magnitude changing here. And Us geotechnical engineers tend to be a little bit on the slow side when things are moving along. But we do appreciate the need to stay saturated. And when the bar opens, we move at the speed of light. I've got many people to thank. I'm not going to start thanking now, but thanks so much, everyone, for coming again. Thanks particularly to Dave, Lydia, Trong, Prash for helping with get everything ready, and Luke for getting everything ready. So I'm going to stop there. I'm sorry I have overrun.
Good evening. I'm Dave Potts, as my name has been referred to, and I'm here to give the closing remarks. Now, my understanding of an inaugural lecture is that basically it's an event to celebrate the fact that someone has been promoted to a professor, has been given a chair. And the audience is extremely mixed. There's people of all age groups. They go from Jamie's Amy to people like me, and perhaps there's a couple of people a bit older than me. There are people from all sorts of backgrounds. There are family members, friends, colleagues from work, civil engineers that have decided that soil mechanics was not their field of expertise, probably because I lectured to them years ago. And decided to do some other discipline, but they vaguely know about soil mechanics and geotechnical engineering, and then there are the geotechnical engineers. And the lecturer, i.e. Jamie, has the task of entertaining and stimulating this mixed audience. That's one objective. The second objective, he's got to convince them that he's worthy of the position that he's been given. And I think we can all agree that it's been entertaining and stimulating, and in a sense, Jamie has ticked all of the boxes. Well done, Jamie. I certainly like the change of clothes and the fact that you... Yeah. I haven't seen you without the hat for a long while. It's a very difficult lecture to give. I remember when I gave mine years ago, I found it very difficult, and I still think it's one of the most difficult lectures I've had to give. We've seen that Jamie's expertise is mainly in field monitoring and laboratory testing, i.e. taking measurements as it looks. Jamie has some admirable qualities, and which we've seen tonight. He has a hands-on approach. He has all the gear. He goes on site. You can see him taking the readings while Wei had a head down the borehole looking at a dial gauge. He can do what he asks his students to do. He doesn't actually ask them to do something that he can't go and do himself. This is in a way a rare talent today, because most academics are pressed to write publications and to write research grants, and it's very easy to delegate some of these tasks. But Jamie is capable of doing all these things. And then another quality that we've seen on the slides, Jamie is prepared to use, dare I say, old-fashioned methods of taking measurements. We saw the dial gauge. We saw the manual leveling. And he does this for two reasons. One is sometimes, as he shows, he gets much more accurate results than using these new fantangled, all-dancing, automatic electronic gizmos. And secondly, perhaps more importantly, he can check that those gizmos are doing the right thing. And this reminded me of an example that Jamie and I experienced some years ago, and I think there's certainly influenced Jamie's way of doing measurements, is that when we were working on the ash embankment problem with Peter Vaughan, and you saw the instrumentation of the movements that were taking place. And bear in mind that when we think about London Underground, we think of tunnels. London Underground trains run on 70 kilometres of embankments, and they were all built by that in the way that was shown on one of Jamie's slides. They're not particularly engineered years ago. They're all past their sell-by date as well. So it was a big problem, and Jamie was involved in putting the instrumentation in. But while we were doing this, we heard of another group that were measuring movements. And this was a group of mechanical engineers. They were academics. And their problem was to do with the fatigue of the wheels on the bogies on the trains. And they were modelling, or measuring, sorry, the displacements of some of the sleepers on the railway line. And we were told that they had this really new system of automatic measurement and relaying it back to the office. So Professor Vaughan dispatched us off to go and investigate. And we went along, and yes, they had a bunch of electro gizmos on the sleeper, which had wires to another box, which had some more electronics in it. And this box sent all the readings off in the ether, and they arrived on the engineer's desk on top of his, in his desktop. And this looked fantastic. There was many advantages to this. You didn't have to go on site. You didn't have to work in the unsociable engineering hours that was often put to you by London Underground. You didn't have to worry about whether you had to drink the night before you were supposed to go on site because of the no alcohol policy. And of course, it didn't take Jamie and I very long to realise that if we had a laptop, we could see these results if we were in a pub. So it had many advantages, and we were quite impressed with this. But of course, while we were there, we were watching the trains as they went past, and you could see the sleepers moving. It was a matter of millimetres that they were measuring. This was pretty obvious. So we were a bit surprised 2 weeks later when we received a report, which when we opened it indicated that the sleepers were moving 100 millimetres. So there must be a mistake. So we phoned these guys up and we said, have you drawn up the graphs to the wrong scale? No. Is the calibration wrong? No, this is it. Well, clearly they were wrong. There's no way they were moving that far, and if they had moved that far, the trains would have all probably derailed, which they didn't. But this is an example of no checks were made independently. No common sense was being applied. They were more interested in how the numbers flew through the Ethernet and got to the desktop than they were about the measurements. And I think this has had an influence on Jamie's work. But having obtained a set of accurate and consistent measurements is not really the end of the story. It's only the beginning. And the important part is interpreting what they mean. And I think we've seen it tonight where Jamie has said, well, you have to put the geological history, the stratification, any sampling disturbance, climate conditions, loading conditions, all these things together and interpret what's going on and come out with what's the mechanisms that's controlling what's going on. It's only then that you can actually stop the problem. It's a bit like, don't deal with the symptom, deal with the cause. The problem is finding the cause is not always easy. And I think it's Jamie's ability to do that has actually set him apart from others and given him an international reputation. And just to take the Crossrail project as an example, Jamie headed that up, all right, it was a team effort, yeah, but Jamie was ultimately responsible for this project. Many papers were published in leading journals, 4 of which were published in Geotechnique, which is commonly accepted as being the top paper for geotechnical research. 2 of those papers were awarded the Telford Gold Medal by the Institution of Civil Engineers. And this medal is awarded annually for the best civil engineering paper published in the suite of journals from ICE Publishing. It is a big accolade to get one of these. I'm sure many academic civil engineers would appreciate getting one in their lifetime. Jamie got 2. It's good to have them. They look good on the CV, and the bean counters like them. But more importantly, they represent the fact that your institution, the professional institution, actually recognises your work as being top quality and actually has advanced the state of the art and, in a sense, advanced engineering practice, which, of course, is what we're all about. As an aside, one of the other papers in Geotechnique, the 3rd one, was awarded the Geotechnical Research Medal by the ICE for the top geotechnical research paper. So the work is of the highest quality, and that is why Jamie, in my view, has got the reputation he has, and well deserved. So I'm going to stop now. I suspect some of you, like me, are extremely unsaturated and in need of resaturation, so, which apparently is outside. So I would like you to join me in thanking Jamie for giving us an entertaining, stimulating, and inspiring lecture. Thank you, Jamie.
Thanks very much, David. So mine is really on behalf of the department and the university to thank you most sincerely for attending. I thought that was a tour de force. Now, if you didn't work out the different attires and so on, now we have your opportunity outside to be able to question Jamie on those different clothes he was wearing. Please join us outside for a drinks reception, and please have it safe when you go back to your homes and so on. So thank you very much for attending, and hope to see you soon.